So, hi students, hope you all are doing well. Welcome to another very exciting session of healthcare entrepreneurship. So, let's get started from where we left last time. Sometimes the critical to quality based products settings or the product features are far more critical to the customers than the other requirements. So, for example, you have this nice thermometer which is looking very nice, sleek, very nice and handy to use, but it is not reading the right temperature. It is showing some huge fluctuation in the temperature. It has everything right but not the temperature. So, this is a bad quality product, right. You will hear the voice of the customer here where people will not take it, right. So, this is the critical to quality part is the temperature, but we have focused our attention into making the nice design to make it very flowery. A very similar example is we all watch movies, and there are so many movies we will see that the star cast is extremely good, and we know as a fact that this movie is very nicely marketed. This is going to really run the show and be very good, and then we go end up watch the movie and we say like this is a complete trash, right. So, next time when I talk to my fellow mates and other colleagues, I'll say the same thing, that this movie they did such a great marketing with, this is a total trash movie, right. So, similar with the products. If a doctor gets a stent which has been built by your company which is faulty, then the doctor will not recommend the other doctors as well as the patients. So, you have lost your business. If there is a wearable device which is tested by certain patients or doctors and they are not liking it for some reason or the other, even the battery meters, smallest things like the battery reading is not very clear, they will send it back, right, and your product is going to fail. Maybe you have spent days and nights, years into developing your product. The only thing you have left to chance is that battery meter. You don't have the lights there that whether the battery is fully charged or half charged. These kind of small things can start a trigger and completely jeopardize the product commercialization, right. So, the critical to quality aspects of your products are very important. What quality aspects, what specific features have to have the maximum quality standards, rest can be there, like very similar, if you are buying a nice high quality car from a well known brand, there could be some quality issues with the chassis and like few other things, but the engine has to be high quality. The car has to be having very nice shockers so that you do not get a lot of vibration on the roads for long drives. So, these are critical quantities, very similar for our medical device. If we have an implant which is going inside as a hip implant, it has to be able to bear the right amount of weight. It has to have the right wear and tear resilience to make sure even after, if this person takes the stairs every day, this person is doing just fine after 6 months. This may not have the right surface texture to do a few things, it does not look good, but it is solving the purpose, right. So, design for quality that way is very important. Critical to quality, going a little further, it basically what this means is, and CTQ is a very well known term in the industry, it is prioritization of the needs of your stakeholders which is needed to ensure time and the money which is spent on subjects with the highest risk. So, basically you have to be very focused here that somebody may be at risk. Even if you feel one person may be at risk, you have to improvise your product, because that one person may start a different journey for your particular product where they have said something bad and things are going off the hill, right. So, a very classic example with let us say cookies. So, you are getting this cookies and cakes from this particular bakery, and there is this one person who has a huge gluten allergy and gluten condition, and this particular bakery is like, oh, this is not a big deal, let us just keep on making cakes, not worry about the gluten free thing, right. So, this person comes here and takes, assuming that this is kind of gluten free or something, and they have branded something, oh, this is gluten free or this is eggless. Very often they would say that, and may have something else, and this is not gluten free to the highest quality, right. So, what happens to this person, and they have never seen this what gluten free or gluten can actually do, and this person eats this cake, a few hours down from there he chokes and he dies, right. and his family files a lawsuit against this particular company, and they are not able to really pay for the lawyers, and this entire bakery just drowns. So, very similar to your medical products, to be very careful while doing this, that the critical to quality aspects are taken care of, even if it is for one person who can suffer, right. If you do not prioritize, you will be drowned in the details. If you are trying to prioritize too much around the marketing, few products do have a marketing aspect, right, like one which has too many competitors, those are the products where you want to have some marketing aspect and things around it, but do not compromise on the critical quality aspect. When is a requirement a CTQ, right? So, how do you know this particular thing is a critical to quality? New, unique or difficult. So, typically when you are trying to solve a problem, so then what you do is specifically look at what problem you are trying to solve for the particular customers. If this particular product is not able to solve that problem and do everything around it, then the critical to quality aspect is not adhered to, right. The problem statements or the painkillers here are the critical to quality aspects, which you find through your value proposition. So, this is the point to emphasize on. It must be guaranteed that the CTQs are met. CTQ requirements are traced through the design activities product element part. So, CTQs have to be met from the design aspects at all the different phases going from the design to production. If you lose the CTQ aspect, critical to quality aspects, then you basically lose, or you are selling a faulty product or not a very high quality product. In manufacturing, for all CTQs a control plan is created. How do you make sure that so many samples, now you are producing hundreds and thousands of this particular implant, how do you make sure the quality is retained? So, if you have to define this is the critical to quality. So, the diameter or this particular radius has to be within this tolerance limits, or the length of the implant cannot exceed, let us say 5.01 millimeters. So, this has to be exactly within that tolerance. If we are able to maintain that, rest of the features will not matter a lot. Let us say there is some surface texture issue, or the color is a little off shaded, or something is a little dark than the others, they are not going to matter, right, because we are maintaining the critical to quality aspect. So, this plan which we make basically when we are into the manufacturing aspect, when we are building a lot of different versions of this, hundreds and thousands of this particular part, defines the checks and the frequencies, like so you have measurements and inspections, and from each product to once per year kind of things, like so you have a particular person who is a quality engineer or a quality check person who keeps on double checking the quality for this particular product which you have built. This is a little difficult to implement if you are in the startup phase, right, but we should still try to do that even if we are making 6 or 10 samples of this product. And as you scale up, hire a quality person who is going to be dedicatedly looking at these measurements and the critical to quality aspects, right, are these tolerances adhered to. And sometimes you can have random checks across the products, and there are so many into the quality control system. That itself is a course in its own, which is quality control and quality and reliability engineering, right. This also ensures that we always produce within the required tolerance window of the CTQ. That's what I just mentioned. Otherwise, you are basically something where you have a voice of customer and the control plan. So, what this figure is showing, they are always chained kind of together. So, if you do not have the right control plan, you will hear the voice of the customer where they will say things are not showing how you promised it to be, right. So, this was back in the day. I used to work with the this bus manufacturing plant in Tata Motors, and they are making majority of the buses there which are plying on the roads in Delhi and other states. So, that is where I got a chance to look into the quality control aspects of things. There is a dedicated set of quality department with several quality engineers, and they are specifically looking at that all the parts are adhering to the tolerances, and all the measurements are within as per, because they do not want even one part to go bad, because otherwise you can, if the buses are produced in a very different way and they are performing differently, they can have a very similar implication to your healthcare products, right. People will come back at you. So, here for the design, during the design for quality, some of the examples thrown here are you are looking at an MRI machine, you are looking at some chip manufacturing plants where this particular chips are designed around with some sensors for measurement of certain parameters from the body. You want to make sure of who your stakeholders are, right? What are the key engineering requirements from a design and value standpoint. You want to look at module or part wise requirement. How many parts do you have in your particular product? You may have a covering which is one part, you may have like screws which are part of that's a single part or set of parts. Then you have so many other aspects which are different components, right? All this put together basically forms the module. Then you have the different process requirements. All this have to go through the different set of processes, right? First is maybe polishing, then painting, and there are so many aspects. Or there could be this different stages of manufacturing where you're using a lathe machine to cut a certain screw shape, and then you have this diameter kind of improvisation and things like that, different machining aspect. So all these processes have to be very clear. So while you're trying to maintain the design for quality, you're thinking of the stakeholders, the engineering requirements, the parts which are there, what are the specific part wise requirements. So many a times you will see this particular screw is not entering this particular place or cavity very well, right? Or the zip is not working very well. That's a poor quality. The parts are not synced well. And the last one is the process, that the same process is qualitatively maintained and done the same way every time, so that the right quality is produced for your product, right? So there are two critical handshakes for each translation. The handshake is kind of essential. So you are basically looking at the review and agreement by the function person that sets them and the function person that implements them. So you basically have the handshakes between folks who are setting the standards, quality standards, and you have another set of folks like who are implementing the standards, right? So you have two kinds of quality people, one who are setting the standards and one who are implementing the standards. So typically you have one set of handshakes to understand the commercial requirements, where you have value requirements, usability, brand requirements, business requirement. It's more from a business or management standpoint. Where you have the product user interaction, where we have talked about UX UI design, the value through the customer discovery, architecture, concept, technology, and the function which the product is built for, right? So these are the commercial requirements where you need to define a particular quality which sets a standard. This is the minimum quality, and how you are going to implement that quality as an entrepreneur, right? The second part is from a technical standpoint, where you have certain system requirements, module requirements, part wise requirements, other CTQs which we have just talked about, critical quality requirements. And part of this implementation process, how this is implemented by another group of folks, is through the maintaining the right supply chain, maintaining the right cost, design for manufacturing techniques, and the right processes, right? So this is how the technical requirements are kind of met. Then you finally have manufacturing requirements, where you set a right control plan, and you have other requirements to make sure your entire manufacturing is consistent and it is going back without any particular retraction. From this aspect, you can think of these pictures, specifically your stakeholders here for this particular MRI machine is basically the patient and the doctors. So if the MRI machine is not working correctly, then both the doctors suffer and also the patient suffers, right? Then you have another component where you have certain system requirements, they have to be met, right? If they are not meeting the certain system requirements, it's not doing very well. Then you have module and part requirements. What are the small modules and parts? Are they upgraded to the latest version or not? Those kind of requirements have to be there in place. Then the next one is process requirement. You want to make sure that all the processes, this is the assembly line for the different components which are going together in this MRI machine, are done with the highest standard of quality, right? Next is you do risk assessment through basically FMEA techniques, so which is a basically manufacturing evaluation technique, design evaluation, process evaluation, and finally what you do is you do a system validation from a stakeholder level, where they have tested it on a few patients or few possible dummy patients to make sure that the device is working correctly and you are getting the right result. You have a system verification, that is it meeting the requirements. So let's say you are getting the scans out of an MRI, right? Are they giving the right resolution? Are they able to detect the different parts of the scan or kind of demarcate the scans, or the right readings are coming from? So system requirements is implemented through system verification, right? So you need to have one set of quality folks who are deciding the standards, what needs to be followed. These are also from the quality engineering group, and another set of people who are responsible for the implementation, right? So the stakeholder is responsible for the device, they do the system validation, system requirements are done through system verification, then the part requirements are read through modular part verification. Modules are separate parts which are forming the smaller part of your bigger system, right? So if this particular chip is not configured, or it is at the with the latest upgraded version, it may throw in a wrong result or wrong calibration work, right? So your system may not start from the zero reading, right? So there could be so many other issues which are there. So you want to make sure these parts are validated. So this is done as an engineer, not at the doctor's level. They are not going to take out the parts and start validating, but this is, if you are responsible for design, development and quality and manufacturing of MRI machines, this is what you need to be careful of, right? Then the process requirement, you want to make sure that the process is cost and time effective and all the parts are with the highest quality standards. So this is kind of implemented through the process verification, where let's say you are trying to build the components for 1000 MRI machines, and you are doing a very sample pilot study for 10 of these machines through understanding of the process verification or validation, right? So this is how you design for quality, by setting standards, quality standards, and implementing the same, right? So this is an example of this FMEA, which is basically the failure mode and effects analysis. Here you're trying to make sure that there are very few failures for all the different aspects, like from the entire device to the individual components to the process. So even if certain assembly lines in your process doesn't work very well, your entire set of parts are not built in the right time frame and with the right cost. If a specific part fails, then it's again a problem. So how much of your parts are actually fail safe, that is what you understand through FMEA analysis. So they do this very detailed charting to make sure the different stages are kind of looked at. So you're here looking at a particular component where the requirement is kind of mentioned, and then you have certain classifications and standards which it is conforming, and then you're looking at how much percentage or how much of that standard is being conformed and it is going right. Whenever you have a red mark, it is basically operator feels like it is not implemented rightly and things are some way out of order. This can be for any of the design quality steps, right? So in order to conclude for designing for quality, we need a proactive building of quality thinking, quality based thinking during your design process itself, and this will go all the way up till the production and commercialization, which will help us to be very successful after the market launch. So if we do all this due diligence and with a lot of patience, our product will actually be very successful in the market. We can design and then build the right product the right way. This is the right thing to do. So the second part is proactively designing quality is about focusing on the most important requirements which are the critical to quality or CTQs, right? If we are careful about the CTQs and putting our 100% attention to them, rest of them could have a divided attention of 80 or 90%. So if we are able to focus on these aspects, we will make sure our product is delivering what it at least promised. Few other things may change, the covering is not very nice, things can change very easily, but if the product functioning is not nice, then it's a huge problem. So, focusing on the important aspects is very important. Then the next part is there are two highly critical handshakes which are done during this to make sure the quality is utmost and during the product development process. One handshake is during the marketing to development. So, basically we are looking at one of the key handshakes where things are implemented from a quality standpoint, and we have defined the right design quality standards. And the next is development to manufacturing. So, development is a process when we do the design and prototyping, right. So, development to manufacturing, again we have to make sure the quality standards are maintained, right, from a setting standard level to an implementation level. So, these two level of handshakes are very important to make sure you have the utmost quality. Welcome to another very exciting session of healthcare entrepreneurship. Today we are going to take a very quick snapshot into design for manufacturing. So, in the previous class we have studied about the quality engineering or design for quality. This time we will get into the design for manufacturing and try to get a very quick understanding of how design for manufacturing is implemented in the device industry as well as the product industry. So, let us get started. So, this is an example where we are looking at a nut and bolt basically, and we are looking at also a washer. So, the question here is which one here is the cheapest component, right. So, DFMA or design for manufacturing is a method for optimizing a new concept or an existing design with respect to manufacturing and assembly by reducing the number of components and processes needed. So, design for manufacturing, basically what it stands for is, let us say we have to develop this particular product for in the healthcare space, and we find out that this is so many electronic components, so many mechanical components, and the total number of components are, let us say, 300. Right. What we do want here is, can we, for the sake of manufacturing and for the sake of scaling this up very quickly, reduce the number of components from 300 to maybe 150 by having a few components integrated? That is where our manufacturing will be much more quicker and cost effective. So, the answer here is, which is the cheapest component in this figure? The cheapest component is the one which does not exist. It is actually the washer. It is the washer which is the cheapest component, but through design for manufacturing, the different stages of it, we will see the washer has now kind of integrated with the nut and bolt. So, you do not need the washer separately to be produced anymore. So, in place of 3 parts, you just need 2 parts, and that gives you a lot of time saving and cost saving, right. So, typically from the drawings, updates, production, storage and assembly standpoint, we want to make sure that the production is not wrong and the assembly is not wrong with so many different components. So, if you have 300 components and if you give the particular set of components to a layman to put all these assemblies together, and let us say the person has changed and is not very trained, he or she may put the particular wires in the wrong places, or may have put the wrong part somewhere else, right. And this happens a lot with a lot of this DIY based devices which we work with. Many of these products are coming DIY if we buy them from Amazon and so many other places, and very often than not we have put the bolt or nut in the wrong places, right. So, that way we are building something which is incorrect. So, if you reduce the number of components and assembly parts, you are able to manufacture very quickly. So, how does the DFM process look like? It basically starts from the conceptualization. So, this is specifically the manufacturing process where we are talking about the concept. We are not talking about the concept of the product itself, right, which is different. That is the ideation stage. This is a conceptualization just for the manufacturing aspect, right. So, that we are trying to scale up a particular product and build 100 or thousands of this. How do we conceptualize this? So, the initial concept here is, for creating a certain joint or put 2 parts together in a particular product, you need a nut, bolt and a washer. The nut basically goes inside the bolt and screws in. that gives the tightness, and you have the washer which is acts as a spacer and also makes sure the nut and bolt after too much of loading doesn't go in, right, and there is not wear and tear. It gives a space for shock absorption, and there are so many aspects which comes along. So this is the initial concept that for this particular task you need a nut, you need a bolt, and you need a washer. Then you analyze this concept and try to redesign by thinking from a design for manufacturing or DFM process outline. And finally, the conclusion is you have now built a new design which is just two components, and where all the three aspects are all integrated in, and the manufacturing becomes much more easier. Let's talk about the conceptualization phase of the DFM process. So here we have a very classic example where we have a a component system where we basically have a cup, a spoon, and we have a saucer, a ceramic saucer on which the cup basically sits in. So we have this three components, right, which is required for serving tea or having some kind of liquid closer to tea or coffee, right. So this is what, let's say, a particular company is trying to manufacture in a large scale. What they have made currently is a design of these three components, and now they want to go for mass manufacturing. So this is the initial concept, which is very clear that these three components are necessary and these are the important aspects. Now we look at the user requirements. During the conceptualization phase, that initial was our assumption that we do understand that a cup with a spoon is the minimum requirement with a base plate or a saucer. Saucer prevents you from getting heat transfer to your body while the cup is very hot with the hot liquid, and the spoon basically lets you stir the liquid if you want to add sugar and whatnot. That's the purpose, right. What is the user requirement here basically? So one of the key user requirement is of course not to hold the hot liquid. So you want to hold it as far as possible, so you need an easy pickup without burning your fingers. So there is this nice pickup which is on the side of the cup typically, and then you have mechanism of stirring without the spilling, like, so basically you have this spoon which you use as a stirrer, and this bottom saucer also prevents from further heat transfer. That is the overall user requirement which is there, and it is consistent with our initial thinking or guess, right. What is the commercial requirement? Commercial requirement is affordable and attractive to the target market. So as we can all think, this cup and plate or spoon thing is very common. All of us have this in our houses, right. Like, we probably have not one set of cups and plates, we probably have many, 4 or 5 sets, right. So what is the key commercial requirement? We want this to be low cost, so that somebody buys it off from, let's say, if they are going to places like Lajpat Nagar or somewhere else, like where these crockeries, these cup and plates are basically sold in bulk, and this has to be attractive. You will not buy this by saying, oh, I want a cup and plate and with a spoon. That's usually not the idea, because you know this is what you need. You want to find something which is really attractive, or which is going to match with the decor of your house, or something which your parents like and whatnot, right. So that's the commercial requirement. So you have user requirements, which are absolutely necessary requirements to get this entire assembly. So you have three components put together in an assembly, and then you have the commercial requirement, which is affordability and attractiveness, right, value propositions here. Then we come to the assembly diagram, where we have this concept which is very, very clear. The conceptualization phase is done. We have understood what we need and what the market needs. Now we do an analysis through the design for manufacturing kind of methods, right. So in the assembly diagrams, what we see basically are the different components, the different processes which are required to build this particular components or put them together, the main assembly and the sub assemblies, right. So what are the three components? You have the first one is the saucer placed on a flat surface. So this is what you are going to place on a flat surface. Second is cup placed over the saucer, it is not the other way around. And third, the spoon placed in the cup. These are the three processes or three steps through which these design components interact, right. Do you have excess of components or excessive processes? This is a valid question to ask from an analysis standpoint, because you want this to be manufactured at a very quick setting, right, quick and cost effective setting. So, further analysis reveals that the components, which is the saucer, spoon, cup, you have an additional component where during the manufacturing which we have not realized quite yet, is the handle. So, typically none of the manufacturing processes here in the market will allow you to build this cup and handle together. It is usually an assembly. So, typically if you have looked at any of the cup or ceramic manufacturing setting, or you have seen how a cup manufacturing actually works, you will typically see the cup is manufactured separately and this handle is kind of then manufactured separately, and this is put together through some addition or through some ceramic bonds and whatnot, right. So, actually what you do have is not 3 components but 4 components. One of this component is kind of a sub assembly to the cup, right. So, do you have excess components? Yes, you have too many components here. Let us look further. So, what are the key processes in terms of the manufacturing? So, this is while you are trying to assemble and manufacture, right, not when you use it. When we are talking about design for manufacturing, we are trying to think how many people are supposed to be there in the manufacturing line, how many steps needs to be there in a manufacturing line, how many processes or steps require a lot of time, what is the overall cost going in every step. So, basically back in the day when I was in the Tata manufacturing plant, we had seen there are several stages of this assembly line, all from working on the sheet metal to making certain like this overall chassis design, to the outer covering which is a different metal, and then there are several processes through which the chassis on that, the tire assembly is placed. So, there are so many steps, and finally you have everything assembled, and then the painting, then the electronics. So many steps of the assembly line. That is why it is known as a manufacturing assembly line. So, for this, coming back to this cup and plate and spoon problem, these are the 4 steps in which the assembly has to be conducted, and that increases the excessive set of processes, manufacturing processes, which needs to be followed for this 4 steps, right. So, what are the key steps here? Basically you have the saucer made by itself, not have to be assembled anywhere. So, it is a standalone saucer which is built, then the handle is built, then the spoon is built separately, and then the cup is built separately, and then you have an extra step, which is step 5, which is making sure you have an adhesive or some form of attachment to make sure the handle can attach with the cup. This is an extra step, right. So, whenever you have this extra step, you need excessive manpower, you need excessive cost, and your time goes up, right. So, the key to manufacturing is basically the time and cost. Whenever we are talking about the prototype, we do not think about these kind of things, right. So, let us say you are trying to build the next product in the healthcare space, which is this particular implant, which is this 4 or 5 different moving components, right. So, you are working with a dental implant, and you have this crown, and then you have the abutment, and then the casing. There are so many components to your dental implants. So, the more and more components, and then you have a screw assembly and whatnot, the more difficult it is to manufacture it. It may look very good on paper while you are trying to design it. It may look very good while you are trying to prototype it, that this is perfect, but when you are trying to manufacture it, it may suck up a lot of cost from your company basically. This is something which you do not want. You do not want to place a huge manufacturing line where there are, in place of 2 people whom you were planning to hire, you now need 10 people to make sure they can manage these sub assemblies and the components, and there is one set of people who can put the adhesive or put the screws together, and there is one person for quality check. More and more people, more and more manpower, the time goes up, cost goes up, you will not be able to afford that scale up, right. So, that is why design for manufacturing is typically, when you are trying to scale up or go in huge numbers, you have to reduce the number of steps as much as you can. So, let us see how we end up doing that. So, we have realized through the analysis that the processes are kind of excessive here. We initially thought of 3 components which turned out to be 4 components, and now we have, in place of 3 processes or 4 processes, we have 5 processes, right. The 4 processes for getting each of the components built, and the 5th process is to put them together, right. So, we need more and more time and cost here. So, typically during the analysis, what we also see is the sequence is basically 1, 2 plus 3. So, basically you need 1, 2 and the 3 overall, right. So, and then you basically work on this assembly, and then you finally say these are all together. Further with the assembly, you look at the sub assemblies which I have already explained, where you basically look at the this cup holder and the cup, which is kind of put together to build this cup. So, the question is, there are 3 elimination based questions. What are the non-essential processes and what are the non-essential components? This is what you need to ask yourself in order to understand or think from a design for manufacturing standpoint. So, the question here is, should the component move or be able to move in relation to the preceding component in the assembly diagram, right. So, the answer to that is no. So, the idea was 1, 2 and 3. So, the saucer, spoon, cup and handle or something like that. Can you just swap them against each other? So, that is one question. So, saucer, spoon, handle and cup. So, this is just this particular, can you move them around? So, you cannot move them around, right. They have to be done in a certain order in the assembly line in order to manufacturing everything correctly. So, while you are trying to make a medical device, let us say you are making an insole with different layers, would you make the middle layer first and then start with the first and last layer? No, that is not the case. You start with either the top to bottom or bottom to top based on the requirement. So, the next question here is, should the component be fitted or removed separately, because otherwise assembly or disassembly of the other theoretically essential components would be impossible, right. So, there are several components which do you want to fit them or have them removed separately? Is that a case? That could be the case for several assembly procedures, that you can maybe quickly fit them in from the side, or they can be done at a later stage. Do you want to do that for this particular problem? And the answer to that is no. If answer to all the 3 questions are known, then basically you are having several non-essential processes or possibly non-essential components which you have not been able to identify. And one of the key things which you are seeing here is the addition here, where the 2 parts have to be built together and they have to be put together again, right. So, here what we need to do here is, after the analysis we need to think about redesigning this. So, this also caters to all your product development endeavors, like we have to identify, to think in a design for manufacturing standpoint, what are the non-essential components and what are the non-essential processes. So, the first non-essential component which I can see, saucer is absolutely important, spoon is important, cup is important. So, the non-essential component maybe is the handle, which we are not thought about initially, and it is a non-essential process where you are trying to put this kind of together, like through an addition. So, the sub assembly, can it be converted into a single component? Very much similar in the lines of the nut bolt kind of mechanism. Can you build this all together? And several manufacturing processes like 3D printing or ceramic manufacturing, like which has certain manufacturing new innovative techniques in place, can possibly do this. So, that is the idea, right. So, basically the old assembly diagram reads something like this, where you have the saucer, you have the spoon, you have the cup, and for the handle you have 4 components and 5 processes, and the new assembly diagram is saucer, spoon and the cup. If you had a technique of building this cup in a single go without have to have this extra processes of putting the cup holder and the cup together and building them separately, you are saving a lot of time and money, right. So, this is the new assembly diagram where they have, how do you actually end up doing it is a separate question, but the point here is having lower number of processes and lower number of components, so that you can quickly manufacture. So, as a conclusion, what you do is you basically have participants, you have a DFMA report, like which is like this design for manufacturing based report, where you do all the stages of conceptualization, analysis, redesigning and conclusion. And then you have several participants who kind of go through the steps and kind of understand the key requirements to this process. Then you have this new assembly process and alternative designs which are out there for evaluation. So, if you had this cup and the holder integrated together, will it perform very similarly to the cases where majority of the cases you have these two components differently, right. So, is it performing very similarly from a manufacturing setting? How much cost or time reduction are you getting? So, this is something to be looked at, right. So, another example with this is basically this is from one of your this jet sprays, like where you are trying to develop the design of a jet spray and you are trying to understand what are the existing problems with it. So, this is from a conceptualization standpoint, you are trying to understand what are the key components of this assembly. This is a very complex assembly which has a nozzle, trigger level, rivet, shaft for different purpose, right. The nozzle is for to transmit the pressure of water. Nozzle basically lets you go from a bigger kind of volume of water to a high pressure by increasing the velocity. Then you have a trigger level which retracts the shaft to control the water flow. And let us think about when we are talking about this particular jet in the lines of a medical device which is going to basically put through some fluids or drug delivery kind of mechanism into the body while performing several tasks and going invasive, right. Then you have a rivet which basically provides a hinge and joins the trigger lever. Then you have a shaft which is basically a connection between the valve spring, shaft washer and nut. So, you have a few comments here where they are trying to do an analysis through the design for manufacturing technique, where they are saying theoretically this nozzle is necessary part since this is the base part. So, handle can be designed to the finger grip. So, there are some comments, critical comments based on expertise. Trigger level theoretically necessary part since this is the moving part. Rivet theoretically not necessary, right. So, this is to understand which parts and components are necessary. So, do we want to start design for manufacturing for existing products out there in the market and start an entrepreneurial journey? No, not really. So, this is for the new products which you are going to develop for your company. You want to go for manufacturing beyond the prototype development, you want to think about all the components. I will give you a very classic example where we were trying to develop this slip testing device, and I have talked about it earlier. This is a portable slip testing device, and we feel like this is around 500-550 components approximately, which have to be built separately or to be purchased separately and to be put together in an assembly. So, all of a sudden we come up with this idea, can we reduce these numbers, because when we have to develop this slip testing device probably 5 or 10 times more, somebody has to be really skilled to do this, and you have so many components which is not fairly intuitive like where they should be, right. So, that is where what can be done is you reduce the number of components. Maybe the design can come in rather than there were sub assemblies, 10 sub assemblies, it can come in 2 or 3 sub assemblies. The motors are now integrated with a controller, right. Some wires are all put together, you buy a wire bunch rather than buying different wires and taping it, right. So, so many components can be put together and you can kind of get also rid of few unnecessary components which may not be the most useful. So, you have certain switches in between which may not be necessary, you just bypass them, right. So, coming back to this example, looking at the shaft, this is theoretically necessary part because it must be separate for reason of assembly. So, we are kind of analyzing this from a design standpoint, what is absolutely important, what is not that important. A water control valve spring, this is usually for the control of water flow through the outlet screw, and the reason this example was taken is because all of us can relate with this, right. We are using a water jet in our toilets and basically our washrooms every now and then, and this is something we can all relate to. If we have not worked with a specific medical device, we may not understand. So, this is just to put your perspective in the same place. So, there are so many components, even many of us may not be aware of this, that this looks like a simple jet, probably 2-step mechanism or 3-step, but this is so many components. We are looking at 13 components. Similar is the case when you go up to your medical devices, right? You may think this just looks like a screw which is a dental implant. There are so many intricate components that there needs to be a certain notch, a certain like angle to a particular thing, and fillets and things which are necessary, which may take some form of your manufacturing efforts, right? So, that is where design for manufacturing helps us streamline. Another thing to notice is it is not always the component, it is also the number of steps which you are taking from a manufacturing standpoint. So, it may be I start with a box, I make fillets, I make some holes. So, these are 3 manufacturing steps I am doing with the same component. This is costing me time and efforts. Again, design for manufacturing is a way to think, can I get something from the market which already has predefined holes and I can quickly do the fillet. That reduces my number of steps. So, when I start thinking from a manufacturing standpoint, I am trying to think for the whole assembly, going from the prototype to something which goes out in the market in bulk. Can I reduce the time and cost? That is the key point, right. So, coming back here, we are looking at few other components like shaft washer, nut. Several of them based on the analysis have been decided to be components which can be eliminated, and there are several components like, for example, let us talk about the inlet washer, which basically prevents leaking at the connection of the nozzle and hose fastener. This can be combined with the nozzle, right, based on the analysis. The hose fastener can connect the nozzle and the pipe hose and combine with the nozzle again. The stopper which holds the compression of spring during clamping can again combine with the nozzle. You are basically looking at the detailed diagram on the left, where let us take a look for a moment. You are basically looking at the nozzle, which is part number 1. So, where do we see part number 1? It is much more inside, somewhere in between you can see. So, part number 1, then you have part number 2, which is basically somewhere else, right. It is the handle, then you have the rivet, which is part 3. Then you have the shaft, which is part 4 towards the front left. Then you have the water divider, which is part number 5. Then you have spring, shaft washer. Several of these components may seem very redundant and mundane, but when you think about your medical implants and devices, this is what you are going to end up with. Lot of parts, lot of components, lot of manufacturing steps, right. Then you have nuts, outer washer, outlet screws, inlet washers, hose fastener and stopper, which is 13 number. 13 is where at, like this is somewhere at the very end on the picture, right. Then you have several components which are put together in terms of a flow chart to show which is going in which direction and what is the assembly order, right. So, this is how your assembly options are kind of generated, that once all these components are there, be ready for the assembly line, this is the order in which things will get assembled, right. So, think about, if I in my phone I have this outer screen, I have these buttons and then I have the touchpad, let us say I have the touchpad, outer screen and then the internal controller and the batteries, right. If I assemble them in the order that I do the touch screen first and then the batteries and then the inside some panel, will it go in the right order? So, everything has to be in the right order and chronology, right. So, that is the assembly, and basically you think about from the design for manufacturing standpoint into all the assembly components as well as to in the order in which they are getting manufactured. Can I reduce the time and cost by combining a few manufacturing processes or few manufacturing components? So, either component or the process can I manufacture or combine them. So, the proposed solution is here, which basically has based on several decision matrix. So, you are basically looking at redesigning solutions. Let us look at the left figure where there is a design concept 1, design concept 2, design concept 3 and design concept 4. So, these are the different design based concepts based on the initial analysis which had revealed that certain components can be combined, certain components are completely unnecessary and few components are absolutely necessary. Based on this, the designers have come out with different innovative designs of getting rid of a few components or combining them together, right. So, let us look at the first design where we are looking at basically having, let us take a also parallel look at the washer. So, yes, so washer had a lot of components. This is the single frame with which several other components are built together. So, you are looking at the handle, you are looking at the nozzle and several components built together. Design concept 2, you have the extra shaft, you have the washer, you have the have a place for pressing force and you have the nozzle, right. Design concept 3, you have several moving components where you have some lock and then the handle, then I see a shaft here as well. Design concept 4, this nozzle, shaft, then there are several other components, end cap, screw, trigger. So, this is again less complex than the real design which we have showcased in the previous slide, but these are much more simplified designs which were built, but everything has different levels of simplifications, right. So, so this is what is there. So, we have to look at from this design from an operation standpoint as well, that it should not be that I have combined so many aspects or so many sub assemblies that this device is not operating the way it should operate. At the end of the day, all it should do is create the right jet speed and it should give the right water movement, right. If you had water flowing in all directions here, it is not very desirable. Would you like to use such a jet in your toilets? Probably not. If you had the speed extremely high, this would hurt your back, right. Do you want to have speed extremely low? This will not do the job, right. So, all the technicalities have to be maintained while we do this design for manufacturing based analysis and design changes, right. So, this has to be assessed very thoroughly, and once this is done, you have a set of decision matrix that which is giving the right operation, and this is probably not very difficult to build. In several cases, there is another thing to point out, right. So, you may from a design, from a theoretical design standpoint, you probably have taken out from 28 components, you have built this to 6 or 7 components, and this outer frame is so difficult to manufacture that you need a very complex machinery, you know, a very high precision 3D printer or high precision CNC machine to build this, which may at the end of the day again enhance your cost. So, you are not building a design just to save time and just to save particular efforts, you are also building a design to save cost. So, all these 3 things have to be put together in perspective: cost, time and basically the efforts, right. If all these things are put together and you optimize them, then you will get the right redesign. So, let us take a look at the proposed solution here. So, you are looking finally at the proposed solution, which is a high quality operating system, which is basically the first component as the nozzle. So, it has been reduced from how many components? There were 13 components earlier in the real design, and you have redesigned it to 8 components based on a detailed decision matrix and making sure that the manufacturing would not be difficult, it would be time friendly, cost friendly as well as effort friendly, right. So, the first one is nozzle, second is trigger lever, the third is rivet, the fourth is shaft. We are looking at all these details. The fifth is a spring, then the sixth is washer. We can see all these components in the right figure, and then end cap and finally the screw, eighth, right. So, much more simplified design, and this is the proposed solution, right. So, the production time has been looked into from a conclusion standpoint. So, part name is here, and part name wise you can look at the original design and the new design. So, what you need to compare is if you had the same shaft or same outer covering being designed and all the parts put together, the entire assembly as well, what is the overall time which is being taken and what is the cost. So, here is an example where for a particular part the production time is being checked for the original design manufacturing as well as the new design manufacturing. So, the time has drastically reduced by 45% from 51.7 hours or 51.7 seconds specifically to 28.3 seconds, right. The reason I took the term hours is because there are certain very high precision devices which may take hours, right. So, in this case it is a second because it is a mass manufacturing kind of a setting. So, 51.7 to 28.3 seconds is a quick turnaround. The handling time, when a person is actually handling the sub assemblies, putting them together and so many other aspects which are done, or taking all the components from one place to another into the assembly line, that has reduced from 14.2 to 8.5 seconds, quite a good reduction, 40%. The assembly time has reduced from 37.5 to 19.8, 47% reduction. So, overall reduction is huge, right. Let us look from a cost aspect, right. So, the cost of the design and of the parts, in the original parts were 13 parts and in the new design you have 8 parts. Number of parts, A parts are similar. The total cost of manufacturing has gone down from 19.62, this could be 19.62 rupees, or it could be dollars, whichever particular currency you are dealing with, has gone down from 19.62 to 10.30%, like almost a 45 to 50% reduction, right. So, this is quite a good reduction in the cost. So, you are looking at this chart on this right, where they are doing a cost analysis going from the original design to the new design. So, the cost has reduced drastically. Even the manufacturing cost, which is the cost of manufacturing each and every component, and the assembly cost. Manufacturing and assembly are two different things, right. Assembly is when you have several components, you put them together or put a screw together or use some form of welding and like other techniques to make them all put together, right. And the manufacturing is a set of different techniques like machining, cutting, 3D printing. These are the different manufacturing techniques. All of these I am going to briefly discuss over the upcoming lectures. So, these manufacturing techniques are usually used to develop certain components or parts, right. So, what has been observed here is both the manufacturing as well as the assembly cost has gone down, which is a really positive thing for the particular product. Specific values which it has come down from is the manufacturing cost was initially 19.62, it has gone down to 10.3, and the assembly cost was 28.64 to 10.46, almost a 1/3 reduction, which is a pretty good number, right. So, that is all for the design for manufacturing. That is the cost reduction, time reduction and effort reduction which you are trying to see. And always apply this design for manufacturing for products which you are trying to mass produce and build in the healthcare space, right. So, stay tuned for more upcoming lectures on the different manufacturing techniques and how we transition from design to product development.